Okay, it's 8:59. So I'll yeah, let's see. Let me see something here real quick. Oh, okay. All right. Well, good morning, everybody, or good afternoon or good evening from where you are in the world. Welcome to day 1 of 4 of the J Champions Conference. My name is Michael Rudlick. I'm a co-director at the Garden State Java User Group, and I have some other titles. I retired from ExxonMobil in June of last year, so it's great. I highly recommend it for everybody. But it's not all about me here today. I'm more than happy to introduce Simon Ritter, who's the deputy CTO, and of course a Java champion at Azul Systems. And so take it away, Simon.
Okay, great. Thank you very much. Right, let me just organize my sharing of screen. Just do that, share that, put that onto slideshow. There. Okay, good. Right, yes, let's get started. So the idea behind this presentation is to talk about, as the title would suggest, keeping your Java hot by solving the JVM warm-up problem. And this is something that's really existed right from the very beginning of Java as a platform, is that it takes time for your application to warm up in terms of performance. So let's start digging into that and understand why we see this particular thing with Java. There are a couple of things we need to discuss in that respect. So the first of those is what happens when you start running a Java application. And you can divide it into, as we see here, sort of 3 stages. First of those is where you start up the JVM itself. JVM is an application, runs on whichever platform, whether it's Linux, whether it's Windows, whether it's Mac, or whatever. It's an application. So that has to start up itself. And there's certain things that need to go on there. Obviously, you've got to load the code of the application. And then one of the other things that's quite interesting is every time you start up the JVM, because it does what's called interpreting, and we'll talk about that in a little bit, it generates bytecode templates for every instruction that we have in the bytecode instruction set. And when I first discovered this, I thought, wow, that's quite interesting that it does that, because surely that's a sort of like a load on the system. But it happens in a blink of an eye. It really doesn't take very much time. And so the idea behind that is that when you run that JVM on any given machine, it will use whatever's appropriate for that machine to get the best possible performance for those bytecodes. Obviously, if you've compiled the JVM to run on an Intel platform, great, that's fine. But there's lots of different versions of Intel processors, and they have different sets of instructions, which might then enable you to do more sort of performant things. So that's why it generates the bytecode templates every time you start up the JVM. So, okay, so now we've got the JVM started up. Now we need to start thinking about the application that we're going to run on top of the JVM. And that then needs to start up. So clearly you've got to do certain things like loading the classes that are responsible for that application. And then once you've loaded those classes and done the necessary analysis to ensure that they don't break any of the security protocols, you then initialize those application classes and make them ready so that when you want to start the application, you can do that. And then, of course, there's some application-specific initialization as well that needs to happen as you start the application up. What we then see is a third phase, which is where we see application warm-up. So we started both the JVM and the application, and now we've got the application running. But because of this fact that we use bytecodes, which are machine instructions for a virtual machine, to get better performance out of that, rather than interpreting them all the time, we use a just-in-time compiler to take frequently used pieces of code, methods, and to compile those as they're running into native instructions. And that way we don't have to go through all the bytecodes every single time. That takes a number of phases because we have what's called the C1 compiler, very imaginatively named, and we also have the C2 compiler, again, very imaginatively named. C1 compiles quickly, C2 will take longer to compile, but use profiling information that's been collected and do it in a more heavily optimized way. What we can also see as the application warms up is de-optimizations. And that's where when we make assumptions about what the code is doing up until the point where we compile it, then we can optimize based on assuming that the code will do the same thing in the future. Sometimes our assumptions prove wrong, so we have to throw away the code and then recompile it. And then obviously the application is doing whatever it needs to do for the work that's involved. Now, if we look at the way that this actually works, the time to first operation, meaning that if you're trying to process transactions, how long it takes to get to the point where you get a single operation and a single transaction processed, is all of the time it takes to start the JVM up and then start your application up. Effectively, that line in the middle there is where you're at the main entry point, if you like, the public static void main. In terms of time to end operations, how long it takes to process a number of transactions, that's a combination of both the time to first operation plus how long it takes to get through that warm up. Because as you warm up, the performance will improve, and so you'll see a difference in terms of how many operations per second can be handled. And again, if we look at these three different stages from the perspective of how long they take, what we'll find is that JVM startup is very fast. There's not really much we can do to improve that. The OpenJDK developers have spent a lot of time and a lot of effort working on improving that. And so that happens very, very quickly. It's very efficient. Application startup, again, is pretty quick. So, there's class loading involved. The more classes you have, the longer that's going to take. So there's certain things you could do as a developer to try and improve that slightly. But overall, it's going to be quick. Application warm-up, that's the thing that can take a long time. What the JVM has to do is it has to profile your application, it has to identify these hotspots of code, the methods that are being frequently used. And in doing so, it can take a long time. If an application does lots of different things, then the ability to find all those hotspots of code can take quite a long time. If it's a fairly restricted functionality, then you might find that warm-up time is quite quick because you're only using a limited set of code and it can analyze that and compile it quickly. So this is what we're kind of looking at as an overall picture. To kind of reiterate what I've just said, what we've got is a virtual machine. So we're dealing with bytecodes in class files. And as we said, we go through these different stages where we initially have interpreted bytecodes. Each bytecode is presented to the JVM each time. We use those sort of templates that have been created to execute each bytecode in turn. There is a little bit of performance improvement that goes on there, only very, very minor, where you'll find that there are certain pairs of bytecodes that happen very frequently together. And so it will generate templates for those pairs. But that's really the only thing that's happening in terms of improving performance. Just-in-time compilation, as I said, the C1 is the fast compiler, but low optimization. C2 is a slower compiler, but generates much more heavily optimized code. So really what you're looking for is to have all of the frequently used pieces of code compiled with C2 and optimized to the maximum level. The problem we see is that every time we start an application, we go through the same process every time. So we have to profile the code, looking for those hot methods. We have to compile them with C1, then we have to use C2, we profile our code, and then we have to recompile with C2, and so on. And what this leads us to is a performance graph that looks typically, I'm not saying every application will look like this, but what we'll see is a performance graph that typically looks like this. On the left-hand side, when we start our application, performance is going to be low because we're just interpreting every bytecode. That's the sort of yellow section there. As we compile the frequently used methods with C1, we'll see an improvement in performance. So things get faster, but not by a lot. And that's the green part there. As we start to take those frequently used pieces of code and recompile them using the profiling information, using C2, we'll see a much better improvement in performance. And so that's the blue graph that we can see, or the blue section of the graph, as it gradually improves. We can see various dips in that graph as well, and that initially in the sloped part is again due to this de-optimization, where we've made an assumption about the way the code works. It doesn't turn out to be true, so we have to throw away the code and recompile things. De-optimization is very bad. We don't like those, try to avoid them. Eventually we get to our steady state, and the dips that we see in performance there are what would be occurring due to garbage collection, if we were using a garbage collection algorithm that needed to pause the application in order to do its work. So the overall shape of the graph, the period of time it takes us to get to this optimum level of performance, is what we call the application warm-up time. Now, again, the problem that we see is that if we analyze the performance, we see our graph on the first run. When we run the application a second time, we see exactly the same thing. So we have to start off from the beginning, we have to analyze our code, compile it with C1, recompile it with C2, and so on. And if we run it a third time, we'll see the same thing again. Every time we run it, we have to do everything from scratch. And that, in many ways, is inefficient. So how can we improve on that? Well, what we'd really like to see is we run the application, let it warm up to the point where we're happy with the level of performance, all the frequently used pieces of code are compiled. When we run the application again, we just get the level of performance that we had when we ran it the first time. And when we run it a third time, we see the same thing. So that's what we're really looking for. Okay, so what I've done is I've broken this presentation down into a number of sections which look at different solutions that you can apply to this problem. And we'll talk about the benefits of these, and we'll talk about the things that are the cons of using these different solutions. Now, the first solution is what a lot of people, certainly in the early days of Java, suggested, which is to say, okay, we like the idea of bytecodes, it gives us our platform neutrality and the right ones run anywhere approach. But surely if I know which platform I'm going to run on, so let's say I'm going to run on an Intel platform using Linux, why don't I just compile my application from Java into native instructions? Use ahead of time static compilation in the same way that I would if I'm using C or C++. That surely is going to solve the problem of warm-up, because now I don't have to analyze the code, there's no interpretation, all of that good stuff. So let's look at this. What could we do here? Well, let's take our code, let's compile it, as I said, using an ahead of time static compilation. We don't have to interpret any bytecode, so there's no problem there. We don't have to analyze to find hotspots, the frequently used methods. We don't have to do any runtime compilation. And that has a double benefit, because not only are we avoiding the problem of the warm-up, we're also avoiding the problem, which is that when we're compiling code at the same time the application is running, we're using the CPU resources and having to share them between application code and transaction handling, if you like, and doing the compilation of the code that is needed by these methods. So we degrade the amount of resources we have available to the application as we do this warm-up. It has a double impact on performance. So if we use native code, we start at full speed straight away. Great. So this is the Graal native image approach. This is something that's been around for a few years now. In fact, it's always interesting to me as somebody who used to work for Sun Microsystems to see the way that Graal has become very popular over the last few years, because this was a project that was actually started back in the days of Sun Labs, and it consists of several different components. You've got the Graal JIT compiler, you've got the Substrate JVM, or Substrate virtual machine, I should say, and you've got the Truffle framework as well. So there's several different components in there, which is what Graal is part of. So the native image approach is the idea of taking your code and compiling it direct to byte to native instructions. So this solves the problem. Surely that's all we need to do. We can just stop the presentation here and say, yes, just use Graal native image. Great. Except not so fast. And I actually mean this in two ways. The problem that we have with using ahead of time compilation is that by definition, it is static, it is fixed. We compile the code before we use it. So we take the Java that's in our source files, we apply the compiler to it, the compiler will parse it, it will do the lexical analysis and so on, generate intermediate representation, pass that to an optimizer and generate compiled code from that. Great. But because it's compiled before it's run, we don't know exactly how it's going to be used as it is running. And that's a big thing. So the compiler has got no knowledge of what's actually going to happen with this code when we do the compilation. Now, there is a way of improving that, and it's something that's been around right from the very beginning of compilers, in fact, which is called profile-guided optimization. What that does is say, okay, use the static compiler, compile your code into native instructions, and then run the application and profile how the application works as you use it. Take that profiling information and then feed it back into your static compiler to give it more understanding of what the code is actually going to be doing when it runs. But that has limitations because, of course, one run of a program may not be the same as the next run, or you may have very varying ways that the application is used. One run is not going to be representative of all runs, so it's limited in what you can actually do with that. To give you some ideas of how this has an impact, let's look at a couple of examples of what the compiler can do if we're using just-in-time compilation versus ahead-of-time compilation. Monomorphic inlining of methods. Here I've got a very simple class called animal, and it has a value that we're storing in there. We're encapsulating the value of the color. Great. So we make it a private instance field, and then in order to access from outside of the animal class, we provide an accessor method called getColor. Wonderful, and it returns the color. If I want to use that in my code, what I'm going to write is my color equals animal.getColor. So I'm calling the getColor method to return the color. What the compiler will do is it will look at that and it will say, right, well, the getColor method only returns the color. If we do what we say in the first line of code and we call the getColor method every time, that has an overhead, because what we're going to have to do is create a stack frame, push it onto the stack to call the getColor method. We then have to take the color method from the object, put it into the stack frame, pop the stack frame off with the result, and get our result back to the calling method. That's inefficient because all we're doing is returning the color. The compiler will look at that and say, I can do better than that. Even though you've marked color as being private, so it's encapsulated, because I'm the compiler and I can do things that are still safe, because I know that all I'm doing is returning the color, I can inline that to say, effectively treat the color instance field as if it was public. Avoid the method call to get color, reference the field directly in the object reference, and take the value from that. So it gives you a better performance because you're avoiding the overhead of the stack frame and the method call. The drawback to this is it only works if you've got one instance or one implementation of the getColor method. Now, Java as a language is dynamic in the sense, not dynamic typing, but it is dynamic in terms of class loading. At runtime, you can load classes as you need them, and you can load classes that overload or provide a different implementation of an existing one. So we could have a different implementation of animal, a different getColor method that does more than just return the color. And that at that point, the code that we've generated is not necessarily valid. If we do that in static compilation, we're in a situation where we can't take advantage of dynamic class loading. There is a lot more that we can do in terms of what are called speculative optimizations. Here's another example using branch analysis. In this method I've got, which is a slightly contrived example, but it does give you a good overview of how these things actually work and what you can potentially do with the compiler. Compute magnitude is my method. I pass in a value, and then I'm testing the value to see if the value is greater than 9. If it is, I'm going to call a method called compute bias, pass the value, and get the value back from that to set what the bias is. If the value isn't greater than 9, I simply set the bias to be 1. And then I'm going to return the log base 10 of bias plus 99. Branch analysis says that when we profile the code before we compile it, and this would be with C2, when we profile that, what we're going to do is we're going to count how many times we go through the true branch and how many times we go through the false branch. When we come to compile this code, if we find that we have never been through the true branch, so the value is 0, then we can rework that code in a more efficient way. And the compiler can actually generate something like this. So we've still got our method called compute magnitude, still takes value. We have to have a test to see if value is greater than 9. We have a contract between us, the programmer, and the compiler, so it has to respect that in terms of that there could be a value greater than 9. If the value is greater than 9, we call uncommon trap. And this is where, as I mentioned earlier, this idea of de-optimization. We've made an assumption about the way the code works and that the value will never be greater than 9. So long as that holds, we're okay. But if the value does suddenly exceed 9, then we've got to say the code we've compiled is wrong. We have to throw it away and recompile. We de-optimize. So if we don't have a value that's greater than 9, the compiler can say, well, the bias is going to be set to 1. 1 plus 99 is 100. And if we're calling log base 10 on a fixed value, we'll simply calculate that once and return it as a fixed value, which is 2. So log base 10 of 100, 2, and return 2. This is great because, as I say, it improves the efficiency of that code a lot. We've avoided various things that are happening there. Simple example, but definitely gives you an idea of what you can do with speculative optimizations. What we've discovered at Azul in terms of the work we've done on JIT compilation is over 50% of the performance gains that we get from JIT compilation are down to speculative optimizations, the things that we can do based on how we predict that the code is going to work. Obviously, that only works if we do have the ability to de-optimize and recompile if something that we've assumed is true turns out to be false. De-optimizations are very bad for performance. You've compiled the code, you run it for a while, now you've found that the assumption you made is wrong, so you've got to throw it away, go back to either interpreted bytecodes or maybe C1 compiled code, and then recompile it. So you're wasting a lot of CPU cycles. So AOT versus JIT compilation, if you just compare those two, AOT means that class loading prevents method inlining. So you can't do method inlining is a very good way of improving performance, but again, with the ability to do dynamic class loading in Java code, you can't necessarily guarantee that the method is going to be the method that you compile ahead of time. You can't do runtime bytecode generation because there are no bytecodes. Reflection is complicated because you have to declare it in advance and the compiler has to be able to deal with that. You can't use speculative optimizations. And so overall, typically, I won't say always, but typically you'll find that the performance of ahead of time compiled code will be lower than for JIT compiled code because of the reasons we just explored. The benefits are certainly that you get full speed from the start. So there's no warm up, there's no analysis of code and so on, and you avoid that whole CPU overhead of compiling code at runtime. The flip side of that, when you use JIT, is you can use aggressive method inlining because you can change the way the code is inlined if you get new classes loaded. You can use runtime bytecode generation. Reflection is, I use the word relatively simple because I don't think reflection is ever declared as simple. You can use speculative optimizations, and overall, again, typically the performance will be higher than ahead of time compiled code. But downside is you've got your warm-up time and you've got the overhead of the CPU to compile at the same time you're running your application. So again, if we come back to our graph here and we look at the typical JIT compiled code graph that we get with Java and the JVM, if we compare that to ahead of time compiled code, we're going to see this. So ahead of time compiled code has performance that's like a flat line, and so it gives you all the level of performance you get right from the very beginning. So that's good. You avoid that overhead of the warm-up, but the typical level you get is lower than with JIT compiled code. Even if you apply profile guided optimization to that, that will raise it somewhat. But again, typically you will still see less performance with ahead of time compiled code, even with profile guided optimization, because of the fact that you can do more in terms of the optimizations when you're looking at code as it's running. So when to use AOT? There are definitely times when AOT makes an awful lot of sense. Ephemeral microservices are a good example of that. So functions, AWT lambdas, AWS lambdas, sorry, not AWT, AWS lambdas, that kind of thing. Where you've got a situation where something is going to run for a very short space of time, then like a microservice that you want to start up very quickly and then shut it down, the idea of AOT is going to make a lot of sense. And indeed, another advantage of very short-lived microservices is garbage collection doesn't tend to be a problem. Because remember, with ahead of time compile code, you've got to compile in the garbage collector to it. That's where the substrate VM comes in terms of the Graal way of doing things. This is certainly good if you've got resource-constrained services as well. If you're running in a 2-vehicle container, then the JIT compilation is going to degrade your performance during warm-up quite significantly. If you've got one core running compiler, only one core running application code versus 2 cores running application code, that's a simple 50% degradation of your performance. Right, let's look at a different approach. If we're not going to use ahead of time compilation, what can we do with JIT compilation to make things better? Solution number 2 is to store JIT compilation data. And this is something that we've done at Azul. We have our prime JVM that does things differently in terms of garbage collection. It also has a different JIT compiler. We replace C2 with one that's based on LLVM, uses different compilation rather than C2. What we do as well is we allow you to store some information. The way this works is you run the application and you let it warm up. You get to the point where you're happy with the level of performance. Could be after a couple of minutes, could be after a couple of hours, could be after a couple of days. It's entirely up to you when you actually take your information. What you then do is you take a profile of the running application, and that's the profile of the JIT compilation information. Essentially, we keep 5 things here. We take a copy of a list of all the currently loaded classes, a list of all the currently initialized classes, which could be a subset of the loaded classes. We may not have initialized all of them at that point. We take all the JIT profiling data that was collected as the system warmed up. So this is all the information that was collected to enable the compiler to generate the code that it did. And most importantly, we record all the de-optimizations that happened as we were warming up. Remember, de-optimizations are bad. So if we can avoid those errors when we start up again, that will help with improving performance. And what we've done more recently is also keep a copy of all the compiled code that was generated. Next time you restart your application, you can specify a link to the files that were collected, so all this information in the profile, and then the JVM can use that to do certain things before we start running the application. Effectively, what it's going to do is it's going to say, right, I know all the classes that were loaded and initialized when the profile was taken. So let's go through and make sure we've got all of those loaded, all of those initialized. And remember, that could be quite a different set to what you get when you just initially run the application. We also know all of the methods that have been compiled at that point. So we can go through and we can look at the code and we can say, right, let's either compile the methods if we need to, depending on what machine we're running on, or let's reuse the code that we had from the last run of the application. So if we're running on the same machine, we should just be able to reuse that code straight away and avoid having to recompile stuff. And we do all of that before we get to public static void main. What that allows us to do is to produce a slight variation on the graph. And what we do here is we say, okay, if we simplify the graph we've seen before, without ready now, we see a sort of gradual warm up to our optimum level of performance. With ready now, we see a much steeper graph. So this is getting much more close to what we've seen with the idea of, statically compiled code, where you start off with instant on kind of thing. Obviously, what we can see here is we've got a much steeper graph. We get to our optimum level of performance much more quickly. Technically, what you would see is that by the time you get to your main entry point, you're going to have about 98% of the performance that you had when you took the profile. There's certain things that we can't do in terms of the way the JVM starts up to get that 100% level of performance. But you will see after 2 or 3 transactions, you'll be back up to the same level of performance you had when you took the profile. Now, the only downside of this is that if you look at the graph closely, you'll see that on the left-hand side, there's a little sort of blank bit where it doesn't do anything. And that's where the JVM is doing all of this work in advance. So it has to load potentially additional classes, has to initialize classes, has to do all the work to make sure that everything is compiled. So there might be a certain period of time where it takes longer to get to actually starting, remember, the application itself, so the main entry point. But we've done a lot of things to alleviate that. Certainly for things like trading applications, this is not a problem, because if you know that you want to start running at full performance at 9 o'clock in the morning, you simply start your application at sort of 5 to 9, 10 to 9, let the JVM do its work, and then at 9 o'clock in the morning, it's ready to go with full level of performance. So as I say, the little blank bit here where we're not doing any application work is class loading, initializing, compile time. Okay, third solution. What about if we decouple? Yep.
Could I interrupt real quick with a question?
Sure. Yeah.
Sure. So I have Crane WWR who asked the question: what is the impact of several util (in quotes) libraries when the same function logic, say my list equals null, or my list dot is empty, and the JIT?
I'm going to defer that question to the end if I can, because I think I need to think about that a little bit, and I want to make sure I get through all the material before. So I'll take that question at the end.
Okay, sounds good.
Okay, right. So solution number 3. What if we decouple the JIT compiler? If we look at the architecture of the JVM, we're going to see something like this in terms of block diagram. At the top, we've got our class loader subsystem where we're doing class loading, verification of classes, initialization, linking, all that kind of good stuff. In the middle, we've got our runtime data area, methods, heaps, stacks, native stacks, and memory, and so on. At the bottom, we've got the execution engine, our interpreter for bytecodes, our JIT compilers, our garbage collector, and so on. And what we did was we looked at this and we said, okay, how can we improve this when we're running, let's say, in the cloud? And what we focused on here was the JIT compiler. So if we look at speculatively optimized code, what we can do is we can actually create a unit of code which has the compiled code for a given method, but it also has a set of assumptions that need to be true in order for that code to work. And if we look at the example that we had earlier, we would say, okay, for the code that we've generated here, we've only got one getColor method that exists, and we have a value that's less than 10. Okay, so these are our assumptions, and the code will work so long as those assumptions are true. What we can then say is that we know from what we've already examined that JIT compilation has a cost. So it's CPU intensive, and it's going to take resources away from the application as we're doing this warm-up phase and we're doing the JIT compilation. Now, if we're running on a powerful machine, if we've got 64 vCores, 64 gigs of memory, we probably don't really notice too much. But again, coming back to the microservice type of environment where we've got 2 vCores, maybe 2 gigs of RAM, it's really going to have a big impact on the amount of performance we can get from the application as we're doing this compilation. It could even result in out of memory errors because we're having to use memory for the compilation at the same time we're running the application, and we don't have enough memory for the heap and the compilation at the same time. So we often end up with a compromise where we have to over provision the amount of resources just so we can get through that first part of the compilation. And once we've got through the compilation, we then have these redundant resources. They're not really being used for the application itself. So again, let's look at some performance graphs and see what we can do here. So take our 2 vCore container example. If we run a simple application on here, the top line of the graph here is showing the throughput. And again, we can see that we've got a nice steep graph. We're warming up very quickly, and we get to our optimum level of performance, and that runs pretty steadily for the rest of the application. If we look at the lower line, what that's showing is its CPU utilization over time. As we start our application and we go through the warm-up phase and the compilation, we can see that we're thrashing our 2 vCore container and using both cores to do all of the work that's involved. So one vCore is probably effectively doing the application, one vCore is doing the compilation. But after we've warmed up, that drops back down, and so we've got a fairly consistent level around one vCore being used. As I said, that shows that we've kind of over-provisioned because we really only needed one vCore to run this application, but we've had to provision two to get the compilation done at the beginning. Now, what we then decided to do was say, right, let's take a different approach to compilation. And that's, as I said, the idea of Falcon, LLVM-based compilation, generates more heavily optimized code. The graphs I've overlaid here show the same application, but now we're using Falcon as our JIT compiler rather than C2. If you look at the top graph, and specifically the right-hand side of that graph, we can see the benefit of Falcon. We're getting, I'd say, roughly 20% more throughput for the same application. We haven't changed any code, haven't recompiled anything in terms of the actual source code. We're just getting different performance because of the way the JIT compiler works internally. But if we look at the warm-up of that application, we can see it's much slower. It's taking a lot longer to get to that higher level of performance. And even once we have got to that higher level of performance, we can see lots of dips in the way things are working because we're doing more aggressive speculative optimizations. And some of those optimizations, the assumptions we made are proving to be wrong. So we're having to drop those out, de-optimize and recompile. And again, if we look at the lower graph, which is our CPU utilization, we're seeing a lot longer that we have to use the full 2 vCores in our environment. And again, when we recompile, we've got spikes as we do that. So overall, it's better from the point of view of the right-hand side of the graph, 20% more throughput, that's good. But the warm-up time, the warm-up effect is more significant with this application. What we said was, okay, well, if that's going to be the problem, why don't we take advantage of the fact that most things are running in the cloud now? Everything's connected as something as a service, and we can communicate between different things over the network, and we can provision whatever we want within the cloud. It's all very, flexible. Why don't we take the JIT compiler out of each of our JVMs that's running and move it into a centralized service, a cloud native compiler or a JIT as a service? If we go back to the graph that we have here, what we're going to do now is we're going to say, right, rather than when we need to compile methods, we will do that locally in our JVM. We'll move the JIT compiler into this centralized service, and we'll send the information about the method that we need compiled, so the bytecodes, plus the profiling information, across the network to our service, have that JIT compiler running in a different instance on the cloud, do the compilation, create the results, and then send them back to us. Now, some people will immediately ask about the issue of network latency and the overhead on network bandwidth and so on. What you'll find is that the amount of bytecodes and the profiling information is very, very small. It's kilobytes of information. So when you're sending it across a high-speed network, it really doesn't matter. It's not a problem. By centralizing it, we can then see what the graph would be like using our remote JIT compiler. And then we get a green line, and suddenly this looks a lot more appealing. And if I drop out the blue line just to make the comparison between C2 running on hotspot and Falcon running on a cloud native compiler, we can see a much better graph or graphs for the results. So now we've got a very similar graph in terms of that performance startup. So we've got a very steep graph, exactly the same as we had with C2, but we're quickly getting to the level where we've got 20% more performance in terms of throughput. And even better is that if we look at the lower graph where we're seeing the CPU utilization, although we got a little bit of a burst of activity at the beginning, which is to do with loading classes and the actual initialization of the application, we very quickly drop off to that same flatline level of maybe 1 vCore of performance. So in this case, we could actually say, right, we don't need 2 vCores because we're not doing any compilation locally. Let's have 1 vCore and save that resource and reduce the amount of money we have to spend on our cloud infrastructure, but still get better performance. So we're getting both better performance and lower resource utilization. Obviously, we have to provision our JIT as a service or our cloud native compiler, but there are other benefits we can get with that. Obviously, people are going to say, isn't that just shifting the cost? Yes, it is, but we're shifting it to a more efficient place. And there's certain things that we can do which make it much better to have it in a centralized service. Centralized service, our cloud native compiler, is going to run all the time in the background. When we start up our application, we pass some methods to it to get them compiled, and we then pass them back as compiled code. By sharing those resources, when another instance of the same application starts up and it runs the same instance or the same application code, when it needs to have the same application or method compiled, passes that to the cloud native compiler, and we can then pass back the same code because we've already compiled it for the first instance. We're caching our code, and that makes things a lot more effective. So what we end up with is this idea of our sort of set of assumptions and our optimized code. And the cloud native compiler can then cache that in a way that when we have a call for a particular method to be compiled, it's effectively doing sort of like a Shazam type of thing, where we've got a pattern matching thing going on to say, okay, it's the same method, but do we have the same set of assumptions in order to verify that this code will do what we want for that situation? And we could have different compilations. So we'd have the same method compiled multiple different ways based on a different set of assumptions. When the remote JVMs call for that code to be compiled, if it matches against the thing that we already have, then we can return it straight away. If it doesn't, we can compile it based on the new set of assumptions, generate a different set of native code, and then pass that to the JVMs as they need it, but still caching that for the next time we need it. We can also do some other clever things in terms of saying, well, heavy optimizations take longer in terms of the overall time to compile code. What we'll do is we'll say, right, return a heavily optimized piece of code as we can do it, but let's then take that same method. We know what we need to compile. In the background, in our cloud native compiler, let's continue running a different way of compiling it that takes longer. We can generate even more heavily optimized code so that the next time we need that piece of code with that set of assumptions, we can return that. Or we could even be preemptive and say, okay, we've now recompiled that method with better optimization, send a signal to the JVM that requested it last time and say, look, I've got a new piece of code for that method. It's more heavily optimized. Here it is. You can load it and use it for your application. Solution 4, let's combine solution 2 and solution 3. So what we did here was we said what we created is effectively what we call the Ready Now orchestrator. We've got the idea of a cloud native compiler, and we've got the idea of Ready Now, which is the profile of a pre-run application. And we've got our cloud native compiler, which means that we've extracted it out and have it remote. So if we combine those two things together, when we want to run an application, it can request a Ready Now profile from what we call our optimizer hub. That can then be used to say, right, we need these classes loaded, these classes initialized, and we need this code compiled. But rather than doing it locally, we can then call the cloud native compiler, which is probably cached from the previous runs we've had of this application when we created the Ready Now profile, and return that code directly so that we've got it immediately available. And that then alleviates all of those different things that we saw in terms of the performance to give us the best possible graph profile for what we're doing there. The last approach that I want to focus on is a new thing that we've been working on for a couple of years now, which is the idea of, what about if we don't just save information about the way the code has been compiled? Why don't we save the whole application state? Now, the idea behind this is that if you think about when you're running, you've got your laptop in front of you and you're running a couple of applications and you've got your web browser open, you've got a Word document, whatever. You close the lid on your laptop and it sort of goes to sleep, doesn't it? Because it's not using the screen and everything. It's just sitting there waiting for you to do something. So when you come back, you open the lid and everything's exactly as you left it. How about if we could do that with a Java application? On Linux, there is a piece of technology called Coordinated Resume in User Space, CRYU, as some people like to say it. And what this does is effectively exactly what I said. It freezes a running application that you've got on your machine. It says, right, so you're running the application. Why don't we just take a snapshot of that? And in effect, pause the program counter. So rather than moving to the next instruction, we stop and we record all the data about the registers, about the stack, about the memory that's in use, and so on, all of that information, and write it out to user space. That's the important thing. So we write it out into a set of user files. Now, I put the simple diagram here, which is a basic von Neumann machine at the bottom. And this is something that we do a lot in the operating system, because if you think about it, the way that operating systems work is about time sharing. In the good old days, when you had a single core, single CPU machine, the way that you could give the illusion of multiple applications running at the same time was to time slice between those applications. So an application would be loaded, its registers, its memory, and so on, its stack would be loaded into the machine. It would run for a certain period of time, and then it would be preempted because you want to run another application, and everything would be saved in terms of its state, the registers and so on, and then the new application would be loaded in. It would run for a certain period of time. By doing that very quickly, sort of milliseconds, you can give the illusion of multiple applications all running at the same time. This is essentially the same thing, but rather than using it to do time sharing at the operating system level, what we're doing is saving the state so that we can reuse it when we restart the application. So we did something similar because we thought, well, you could use that with JVM on its own. Don't do anything at the Java level. Let's just use Cryo, treat the JVM as an application, create a snapshot of that running application, write it out to a set of user level files, and then restart it from that point. Which is fine, except there are all sorts of problems that become apparent when you try and do that. Because if you restart the application from the exact same point, if you've got things like open file descriptors or network connections, or even like using the time for a cache or something like that, when you restart the application, certain things may have changed in the period between when you had the application running and when you restored it. Things like file descriptors or files may have changed or may have disappeared, network connections may have timed out, all those sorts of things. So it becomes very difficult just to treat the JVM as the application and doing a Cryo type of checkpoint on that. So what we said is, okay, let's still do that basic idea. Let's treat the JVM as the application, create a checkpoint on that, but let's up level it so that the JVM and the Java application actually understands that it's being checkpointed and restored. That's the coordinated part in Crack. Our application's running, great, and then we decide at some point we want to make a checkpoint. We tell the application that it's going to be checkpointed. And that way it can take action to prepare for the checkpoint. And that action will be things like closing file descriptors so that we tidy those things up, and potentially even taking a sort of cyclic redundancy code of a file. So you've got a checksum to be able to determine if the file has changed when you come back after a restore. Similarly, with network connections, you can shut those down. You can take account of the time, record that information, any other things that you need to do to tidy up before the checkpoint is created. Create the checkpoint, and then at some time later, we want to restart our application. The coordination says that before we actually start the application doing any work, we make it aware that it's being restored. That way, it can then say, okay, I need to reopen this file descriptor so it's available for the application to continue. I will check the checksum. If it's changed, I need maybe take some action to reload the file or do something with the data that's in the file. Same thing with network connections. I can restore those and take account of the change in time to make sure I don't invalidate my entire cache and things like that. So Crack enforces some restrictions on the checkpointed application. So it won't allow you to create a checkpoint if you've got any files or sockets open. It just won't allow you to do that because it's the simplest way of making sure that we do have reliable restarts of our application. How this works is through a very simple API, and what you do is you say any of the classes in your application that need to be made aware that they're going to be checkpointed or restored, they implement a simple interface called resource. Resource has two very cleverly named methods, before checkpoint and after restore. I'm sure you can guess what you do in those. So the way that it works is that you will register your resources with the JVM to ensure that it knows about all the things that need to be called as the checkpoint is created and after restore is done. And the way that this happens is that you can provide an order for that. So you specify the order in which the resources will have the before checkpoint called. So you've got 3 classes A, B, C. You can specify that the order of the checkpoint is done for the before checkpoint for B, C, and A. When we come back doing the restore, the reverse order is used. So it will be A, C, B, so that you're going down one way and then coming back the other way, so that you've got the restore happening in a predictable way, in the same way that the checkpoint is created in a predictable way. As I said, simple API, so you get a before checkpoint and after restore for the resource interface. You then use a context to register the resources with the JVM, and the context you can get from a class which we call core, which has a global context associated with it. If you want to, you can create your own context, but most people are just going to use the global context. So it's very simple, very straightforward. Really, as a developer, what you're doing is working on the code that needs to be produced for the before checkpoint and after restore. Using the crack API, as I say, you create you get the context, you add the methods, add the classes in terms of the resources, you implement the before checkpoint and the after restore method, and gives you a nice predictable way of doing things. Does it work? Well, the answer is yes. Here's some benchmarks we did. What we did was we took some simple applications. So let's talk about Spring Boot here as a good example, because crack has now been implemented and integrated into Spring. So you can actually use it now if you want to with the most recent release of Spring. It's there available. You don't have to do any extra work to use it. So Spring Boot, we took a simple application and we ran that from cold to see how long it would take to get to first operation. In the case of the machine we were running on with the code that we had, it was about 4 seconds. When we took a snapshot of that using crack and restarted it from exact same point so that we could continue doing the work of the application, even with the overhead of the loading all the files and so on, and doing the after restore, making sure everything is as it should be, 38 milliseconds. That's 2 orders of magnitude faster. We've tried it with Micronaut. Again, similar kind of improvement in performance, 2 orders of magnitude. Quarkus, same thing. XML transform, probably not a great example, but the 3 there, Spring Boot, Micronaut, and Quarkus, all very good examples of this. Just to summarize then, solving the JVM warm-up problem. The simple answer is there isn't a single solution that fits all situations. So you need to look at what's available and think about how to get the best from that. AOT is very good if you want fast startup, small footprint, and ephemeral services. But the downside is you may not get as good performance as you get with JIT compilation. So you're sacrificing overall performance for speed of startup. Ready Now provides you the memory across JIT compilations, but you've potentially got this sort of period of time when the application doesn't do anything as it's doing all the work before it gets to the main entry point. Cloud Native Compiler offloads JIT workload. That's good. So you avoid having to have the additional workload on your machine. But again, you've got to then pass things across the network. So there's the issues of, if the network fails or whatever. We do still have the JVM in the we do still have the compiler in the JVM, so if it needs to, it can do it locally if it can't contact Cloud Native Compiler. Ready Now Orchestrator, combine both Ready Now and CNC, so it gives you kind of the best of both worlds. And crack is great if you're looking at, starting an application from a known point. If you like, the downside of crack is that we have to store all the state of the machine, obviously. And what that can be is that if you have a very large heap, then we've got to write the whole heap out to a file. Now we have some ways of improving that in terms of doing a full garbage collection on the heap first, so we only write out what is valid data. But if you have got a very large data set, that's going to take time to write out. It's going to take time to read in. There is also Project Leiden, which is an OpenJDK project. I would say that crack is an OpenJDK project as well. Project Leiden is one that's looking at different approaches to how to improve startup of JVM performance. So it's something to keep an eye on. They haven't really published too much about what they're doing at the moment. Okay, so that's it for slides. So let's go back to that question that we had.
Yeah.
So I can see if I can
Want me
answer
to
that.
reread it, or can you see the chat?
Yeah, you definitely have to repeat that.
Okay, sure. So we had a flurry of questions in the crack section there. So,
Okay, yes.
so yeah, what is the impact of several util libraries with the same function logic? Something like my list equals null, or my list dot is empty, and the JIT.
Right. So the JIT is really quite clever, and I think what you're saying there is that the JIT will take into account what's going on, and as I said, you can potentially get different compilation of the same method, but with different assumptions for how the speculative optimizations work. So I think that's probably the easiest thing to say there is the JIT is very clever. If you look at the code that's generated by the JIT, it really does work very well. It's gone through a number of years of development, and it's very sophisticated in what it can actually do.
Awesome. And Cole had asked during your session on crack, it's the same as Apache Flink to maintain state.
Yeah, because I'm not really that familiar with Flink. Is that Kafka related? Is that a Kafka related thing?
Yeah, I've heard of it. I've seen a couple of presentations on it, but
yeah, I think I'm probably going to pass on answering that question because, like I say, I'm not familiar enough with Flink to be able to do a comparison between what that does and
I know somebody who's very familiar with Flink. Perhaps I could pass that question on.
Yeah.
So, and then Luan asked a couple of questions. So, first says, thanks for sharing it. Should we do the checkpoint before any real operation because all states of the operation will be restored? And then, for example, a 4 will be restored in the same index in the time that we did the checkpoint.
Yes. Yeah, so this is something that you can decide yourself. So there's two kind of approaches you can take. First is you can say to yourself, okay, let's take advantage of the fact that we know that there's a lot of work goes on to actually get the application ready to handle transactions. So let's get through all of that, load anything in terms of data that we need to process and so on. And then before we start handling transactions externally, let's take a crack snapshot at that point so that we can restart it very quickly to get to that sort of beginning of the application. But the other alternative is you can, if you want, say, right, you're in the middle of an application. Excuse me. Oh, voice is giving out. You could say, okay, well, I'm at a particular point in my application, and I really want to take a snapshot here so that I can start from that exact same place. So it's very, very flexible. And it's entirely down to what makes sense for your particular situation as to whether you take a snapshot at the beginning of the application or at some point where you've done a certain amount of transactions or so on.
All right. Next question is, what are the differences between Ready Now and class data sharing?
Yes. Okay. So class data sharing is all about when you start an application, classes get loaded and initialized, and that builds a set of data structures internally within the JVM. So when you do that, every time you start up the application, you do the same thing. So the class data sharing is about saying, okay, once you've done the class loading and the class initialization, take those internal data structures, write them to an external file. Next time you start, rather than having to do the class loading and the class initialization, you simply map that file into memory, point the JVM at the right point in that file, and you've immediately got that information ready to go. Ready Now is more about compiled code. So it's to do with the JIT compiler rather than just class loading and class initialization. So it's two orthogonal things there. One is class loading and initialization. Even though Ready Now also deals with that, you can combine Ready Now with class data sharing to get even better results.
All right. Yeah, that question was from Anthony, by the way. So there was Antonio had asked about it working with all operating systems. I had Well, I answered it somewhat. I wasn't 100% sure, but then Frank Delport actually answered it about working on all operating systems.
Yeah, so right now it only works on Linux.
Yeah.
That's because we use cryo underneath as the way of doing the persistence of the state of the JVM. But it's the important thing to understand is that even though we use cryo, it's not tied to cryo. We could use different ways of doing things, and in fact, we do it slightly differently in Docker containers, for example. But Windows and Mac don't have a similar default piece of functionality like cryo on them. So there's no way of doing a simple snapshot of a running application on Windows or Mac. But that doesn't mean we can't do that. In fact, we are looking at how to implement this on those platforms. But it's quite a lot of engineering work, and we haven't quite got to that point yet. We're still making sure that crack is popular enough for us to invest that sort of work into making it work cross-platform.
And James Lynch has asked, have you tried running the engine in the QEMU emulator to see if bytecode compression techniques have an effect?
No, well, not that I'm aware of. That's quite a specific question. No, I don't believe we have tried that.
Let's see.
It's a good idea, though. We should try that.
Let's see. So is there something unique about Java that make the startup problem a recurring conversation versus other languages where it's not mentioned much? And this is from Michael Remajan.
Yes, it's simply the fact that Java uses a virtual machine. So the same thing, if you like, applies to things like .NET, because you've got the common language runtime. So it's a similar kind of concept of using a virtual machine in effect. So anything where you've got a virtual machine and you have to convert from virtual instruction set to native instruction set, you're going to see a problem with warm-up time or overall performance, because if you go back to the very beginning of Java where they didn't have a JIT compiler, you got much lower performance with a Java application compared to a natively compiled application. So you won't see it with any application code. So C and C++, you never hear about warm-up time because it just isn't an issue, because there isn't any warm-up from the point of view of the code itself. It's already pre-compiled. Warm-up time in those situations is more to do with the application code.
And last is a request to sharing the benchmark repository with the Quarkus example.
Yeah, it's already there. It's on GitHub. If you go to the OpenJDK website and you look for crack, there's a link from the crack page on OpenJDK to the GitHub repository that has all the benchmarks in it, so you can try it there.
Yeah, and I think that's it. I think that's
okay,
it for everybody. This was
Great.
an awesome session, Simon. Thank you very much.
Thank you.
So I guess there's nothing else. Then we'll see you at the next. We'll see everybody at the next session.
Okay, thanks a lot.
All right,
bye for now.
Thanks. Okay, end the stream.